Hello everyone. Today we will solve numerical problems based on rectangular waveguide. So, our first problem states that a rectangular waveguide with dimensions A equals to 2.5 centimeter, B equals to 1 centimeter is to operate below 15.1 gigahertz. How many TE and TM modes can the waveguide transmit if the guide is filled with a medium characterized by sigma equals to 0, epsilon equals to 4, epsilon naught and mu r equals to 1. Calculate the cutoff frequencies of the modes. So, to start with, we know the cutoff frequency is given by f of c mn equals to mu prime by 2 root over of m square by a square plus n square by b square. Okay. So, the cutoff frequency is given by c equals to u cap by 2 root over of m square by a square plus n square by b square, where m and n are the indices for the modes. So, we are given that A is 2.5 centimeter and B is 1 centimeter. Okay. So, we can write A upon B is 2.5. Now, u cap is given by 1 upon root over of epsilon mu, that is equal to c upon, where c is the speed of light, c upon root over of mu r epsilon r. So, in this case it is c upon 2. Hence, we can write f of c mn as c upon 4 root over of m square by a square plus n square by b square. That is, in place of mu naught we are substituting c by 2. So, FCMN comes as c upon 4 root over of m square by a square plus n square by b square. This can be simplified as c upon 4a root over of m square plus n square times a square upon b square, which can be written as c upon 4a m square plus n square times, so a by b was 2.5, right. So, we will substitute in place of a upon b as 2.5 square. Now, substituting the values, we will get c, we have 3 multiplied by 10 to the power 8 upon 4a. So, a is 2.5 centimeter. So, 2.5 10 to the power minus 2 root over of m square plus 6.25 n square. So now we get 3 root over of m square plus 6.25 n square gigahertz. So this is equation 1. So we get Fc as 3 m square plus 6.25 n square. Denote this as equation 1. Okay. Now we need, like, here it's given that we need to operate the waveguide below 15.1 gigahertz. Okay. So it's needed to be that FCMN should be less than 15.1 gigahertz. Okay. Now a systematic way of doing this is to fix m or n and then increase the other until FCMN is greater than 15.1 gigahertz. Okay. So what we will do, we will first fix m and then we will fix n. Okay. So first fixing m, we get, like, for m equals to 0 and n equals to 1. Okay. Suppose we are getting TE01, for TE01 mode we will get the cutoff frequency as FC01. So from equation number 1 we will substitute the values of indices m and n in equation 1 and then it will yield us FC1 as 7.5 gigahertz. Okay. So in equation 1 we are substituting first m0 and n1 and therefore for TE01 mode we are getting FC01 as 7.5 gigahertz. Okay. So we are now fixing m. Okay. So now the next will be m is 0, n is 2. Okay. Therefore for TE02 mode we will get f of C02 as 15 gigahertz. Similarly for M0 N3 we will get FC03 as 22.5 gigahertz. Okay. So 22.5 is coming greater than 15.1. Okay. So we can say that maximum n can be 2. So to conclude we can say thus maximum n is 2. Now what we will do? We will now fix n and then change m. So now we will fix n and change m. Okay. Therefore for TE10 mode, we will have f of C10 as 3 gigahertz. Again this we are getting from equation number 1 for the indices m1 and n0. Okay. So now we will again change to the next value, that is for TE20. So for TE20 mode f will be f of C20, that is 6 gigahertz. Similarly we can find out for TE30 we will have 9 gigahertz. For TE40 we will have 12 gigahertz, TE50 we will have 15 gigahertz, and then for TE60 we will have 18 gigahertz. Okay. Now, this TE50 when FC50 is 15 gigahertz, this is same as TE02. Okay. Therefore, from above we can conclude that maximum M is 5, because 18 gigahertz is again greater than 15.1. Okay. Now, what we know, that we know the maximum M and N. Now, we will try the other possible combinations in between these maximum values. Okay. So, since we know the maximum values of M is 5 and N is 2, we will try some other possible conditions in between these maximum values. Okay. So, we will have TE11 and TM11, which are the degenerate modes. Okay. We can write FC11 as 8.08 gigahertz. For TE21, TM21, FC21 will be 9.6 gigahertz, TE31, TM31 we will have FC31 as 11.72 gigahertz. For TE41, TM41 we will have FC41 as 14.14 gigahertz, and for TE12, TM12 we will have FC12 as 15.3 gigahertz. Okay. So, now those modes whose cutoff frequency are less than or equal to 15.1 gigahertz will be transmitted. Okay. So, among all the possible conditions, we can see that 11 TE and 4 TM modes are possible. Okay. So, the next problem. So, for the same waveguide as in question 1, we need to calculate the phase constant, phase velocity and wave impedance for TE10 and TM11 modes at the operating frequency of 15 gigahertz. Okay. So, from equation 1, okay, so we had Fc for the same waveguide, we had Fc as 3 multiplied by root over m square plus 6.25 n square. From there we calculated that for TE10 mode Fc was 3 gigahertz. Okay. Now, first we need to calculate phase constant. Okay. So, phase constant is given by omega square root of mu epsilon times 1 minus Fc upon F square. Okay. So, substituting the values, we all know the given values. The operating frequency is 15 gigahertz. So, f is 15 gigahertz. So, we will substitute. We have omega as 2 pi f, and then we can write mu naught epsilon naught mu r epsilon r put over 1 minus f c upon f square. So, 2 pi f upon c, epsilon r we had 4. So, square root of 4 is 2 multiplied by 1 minus cutoff f c is 3 and operating frequency is 15. Okay. So, that will give us 615.62 rad per meter. Next is phase velocity. So, phase velocity is given by omega upon beta. So, 2 pi multiplied by f is the operating frequency. So, it is 15 gigahertz. So, 15 10 to the power 9 upon beta will calculated as 615.62. So, this will yield 1.53 into 10 to the power 8 meter per second. Now, the wave impedance. So, wave impedance is given as so substituting we will get mu naught 4 epsilon naught 1 upon 1 minus f c was 3 by 15 square, that gives us 192.4. So, this was for TE10. Similar thing we need to repeat for TM11. So, for TM11 we will have Fc as 1 upon 2 epsilon naught m square upon a square plus n square upon b square. So, this will give us c upon 4 1, a was 2.5 centimeter. So, 2.5 10 to the power minus 2 plus n is also 1 and b was 1 centimeter. Okay. So, this gives us 8.07 gigahertz. Okay. Now, phase constant beta, the same thing. So, phase constant beta will be, so 2, it was omega mu epsilon. So, we can write it as 4 pi f by c, 4 pi f upon c like the previous one. So, 1 minus In this case Fc is 8.07 and F is 15. So, Fc by F square. So, phase constant we get as 529.4 rad per meter. Now, phase velocity. Phase velocity is omega upon beta. So, substituting we get 1.78 to 10 to the power 8 meter per second. So, this is the phase velocity, and next is wave impedance. So, wave impedance we have one minus Fc upon F square. So, again substituting we will get 158.8 ohm. Okay. Now, the next question. The third question says that an air-filled 5 by 2 centimeter waveguide has Ez as 20 sin 40 pi x sin 50 pi y e to the power minus j beta z volt per meter at 15 gigahertz. So, we need to find out that what mode is being propagated, and the second is find out beta. Okay. Okay, so here Ez is non-zero, therefore, it is a TM mode. Now, it is given that Ez is 20 sin 40 pi x sin 50 pi y e to the power minus j beta z. Okay. So, we will compare this with the generalized one, that is E naught sin m pi x upon a sin n pi y upon b e to the power minus j beta z. Okay. So, comparing this and this, these two equations, we will get E naught as 20 and m pi upon a is 40 pi, which gives m as 40 a, and since the dimensions of the waveguide are given, so m comes out as 2. Okay. And again comparing the above two equations, we get n pi by b as 50 pi, therefore, n we can write down as 50 b. On substituting the value of b like 2 centimeter, we get n as 1. Therefore, the indices are 2 and 1. So, TM 21 mode is being propagated. Now, the second one, so this is A, TM21 mode is propagated, and again we need to find beta. So, beta we know, beta is given up by omega mu epsilon 1 minus Fc upon F square. Okay, so first we need to find Fc. So Fc we can write down as 1 upon 2 mu epsilon root over of plus n by b square. So substituting the values, we will get 3 into 10 to the power 8 by 2. M is 2, A is given as 5 centimeter. So 5 into 10 to the power minus 2 square plus n is 1. So 1 upon 2 into 10 to the power minus 2 square. So this will give us Fc 9.60 10 to the power 9 Hertz. Now substituting the value of Fc in beta, we will get beta as 1 minus, so Fc is 9.60 and F was 15. So we will get beta as 241.3. Okay. The next problem. Okay. So in an air-filled rectangular waveguide, the cutoff frequency of a TE10 mode is 5 GHz, whereas that of TE01 mode is 12 GHz. Calculate the dimensions of the waveguide, the first one. The second one is we need to calculate the cutoff frequency of the next 3 higher TE modes. And the third one is the cutoff frequency for TE11 mode if the guide is filled with a lossless material having epsilon r equals to 2.25 and mu r equals to 1. So we know for TE10 mode we can write Fc as C upon 2A, substituting the value for C, this one. Okay. Now it is given that for TE10 mode the cutoff frequency is 5 GHz. So we can write down that 5 GHz is equal to this one. From this we can calculate the value of A and this comes out as 3 centimeter. Similarly for TE01, so for TE01 we will get Fc as C upon 2B and thus we can write for TE01 the cutoff frequency is given in the question as 12 GHz. So we will write 12 GHz is equal to C upon 2B. So we will get value of B as 1.25 centimeter. Now since A is greater than B, okay, since A is greater than B, the next higher order modes are calculated as, so we can make out a table like this. So this is the mode and this will be the cutoff frequencies. Okay, so we'll start again with TE10, the cutoff frequency with 5, then TE20 it's 10, TE30 it's 15. So these are all in. Again say for TE40 the cutoff frequency is 20, for TE01 it's 12, for TE02 it's 24, and for TE11 it's 13. Okay, so we need to calculate the cutoff frequency of the next 3 higher TE modes. Okay, so in the question, like it's given that for TE10 mode it's 5 gigahertz. Okay, so the next we need to calculate the next 3 higher TE modes. Okay, so these are all in gigahertz. Okay, so greater than 5 it will be the next 3 higher order modes, the next 3 higher TE modes will be TE20. Okay, so 10 and then 12, that is TE01, and then 13, that is TE11. Therefore, we can say like the next 3 higher order modes are TE20, TE01, and then it's TE11. Okay. The next part says the cutoff frequency for the TE11 mode if the guide is filled with a lossless material having epsilon r as 2.25, mu r as 1. Fine. So we will write down like Fc is prime upon 2 m square upon a square plus n square upon b square, where u prime is 1 upon mu epsilon, that can be written as 1 upon that is 1 upon .25, and thus substituting the values we will get it as 200 10 to the power 6 meter per second. Therefore, Fc is .2. Substituting for m and n and a and b, we will get 1 upon square plus 1 upon 1.25 into 10 to the power minus 2. So these are the indices, modal indices and the dimensions. So we will get Fc as 8.67 gigahertz. Okay, next question. Calculate the dimensions of an air-filled rectangular waveguide for which the cutoff frequencies for TM11 and TE03 modes are both equal to 12 GHz. At 8 GHz, determine whether the dominant mode will propagate or evanescence in the waveguide. Fine. So now again to start with, we will start from cutoff frequency, that is Fc, is given as this equation, where u prime is 1 upon mu epsilon, since this is air filled. Okay. So, we will get Fc as C upon 2 root over of m by a square plus n by b square. Okay. This is the cutoff frequency. So, it is said that we need to calculate the dimensions of an air filled waveguide for which the cutoff frequency for TM11 and TE03 modes are equal. Okay. So, now we will calculate for TE11. So, it comes out as, substituting the values, we will get, so m is 1, n is also 1. So, 1 upon a square plus 1 upon b square. Okay. So, this is given as 12 gigahertz. Okay. So, we will write down we will write 3 into 10 to the power 8 upon 2 root over of 1 upon a square plus 1 upon b square is 12 gigahertz. It is given in the question. So, this is our equation 1. Similarly, for Fc03 we will get one more equation, that is 3 into 10 to the power 8 upon 2 root over of 3 upon b square, for this is for TE03. Okay. So, this is also 12 gigahertz. So, we have two equations and we need to find out the dimension of the waveguide. So, two equations and two unknowns. So, what we will get? So, from equation 2 we get, we can write and then we can have b as 3.75 centimeter. Okay. Now, substituting the value of b as 3.75 centimeter in the other equation, we will get a as 1.32 centimeter. Okay. Now, since a is less than b, therefore, the dominant mode is TE01. Okay. Now, if it is TE01, then what will be the Fc? So, f of C01, we will have C 3 into 10 to the power 8 upon 2b. So, 2 into, we have b as 3.75 centimeter. Okay. That is 4 gigahertz. Okay. So, the cutoff is 4 gigahertz, which is less than 8 gigahertz. Okay. And therefore, the dominant mode will propagate. So, 4 gigahertz, this is less than 8 gigahertz. So, we can comment like that, dominant mode will propagate. Dominant mode will propagate. Okay. Next question. The next question says that 1 centimeter cross 3 centimeter rectangular air filled waveguide operates in the TE12 mode at a frequency that is 20% higher than the cutoff frequency. Determine the operating frequency, the phase and group velocities. Okay. So, we will start solving. So, in the given question there is 1 centimeter cross 3 centimeter rectangular air filled waveguide, okay, and it is operating in TE12 mode and at a frequency which is higher than 20% of the cutoff. Okay. So, we will start with cutoff frequency. So, Fc will be this equation. Okay. So, while substituting the values for m and n, we can write 1 upon plus n is 2 and b is 3 centimeter. Okay. So, Fc will be 18.02 gigahertz. Now, it is given that the operating frequency is 20% higher than cutoff frequency Fc. Okay. So, we can write F, that is operating frequency, is 20% higher than Fc. So, it is 1.2 F of c. So, Fc, so 1.2 Fc is 21.63 gigahertz. Okay. So, the operating frequency is 21.63 gigahertz. This is subpart A. Now, subpart B. We need to determine the phase and group velocities. Okay. So, phase velocity is given by c upon root over 1 minus Fc upon F square. So, we know all the values. So, on substituting we will get phase velocity as 5.427 into 10 to the power 8 meter per second. This is the phase velocity, and group velocity we will calculate it as c square. So, upon Vp. So, this is 3 into 10 to the power 8 square upon Vp is, just now we calculated like 5.427 10 to the power 8. So, we will get 1.65 into 10 to the power 8 meter per second. Okay. So, phase velocity and group velocity is done. Next question. So, the next question is, a microwave transmitter is connected by an air filled waveguide of cross section 2.5 centimeter cross 1 centimeter to an antenna. For transmission at 11 gigahertz, find the ratio of the phase velocity to the medium velocity. Okay. So, a microwave transmitter is connected by an air filled waveguide of cross section 2.5 centimeter cross 1 centimeter. Okay. So, again we will start with calculating the cutoff frequency. So, Fc is, we can write like 3 into 10 to the power 8 upon 2 root over of m upon, so it's 2.5 centimeter. So, 2.5 centimeter square plus n upon, so this is the cutoff frequency. Now we can solve it like m square upon plus n square. That gives us 15 root over of m square upon 2.5 square plus n square. Okay. Now we need to check for transmission at 11 gigahertz, find the ratio of phase velocity to medium velocity. Okay. So we'll start with FC10. We will have it as 6 gigahertz. Okay. FC20 we will have 12 gigahertz and FC01 is 15 gigahertz. Okay, but the transmission is for transmission at 11 gigahertz. Okay, so only which one will propagate? Only TE10 will be propagated. Okay, so only, therefore only TE10 mode is propagated. Okay, and then we will find the ratio of phase velocity to the medium velocity for this mode. Okay, so phase velocity, we know it is given as c upon 1 root over 1 minus fc upon f square. Okay, so ratio of phase velocity to medium velocity, because since it is air filled waveguide, so it will be Vp upon c is 1 upon root over 1 minus fc upon f square. Okay, so this ratio, so now we know fc. Okay, we also know f, so this we will get substituting, after substituting the ratio comes out as 1.193. Okay, so thank you, this is all for today.